Hey, my friend, tonight, let's set everything down, the to-dos, the noise, the hurried clock, and slip into a quieter room inside your mind. Not to race through science, but to float with it. We'll wander gently into how time really works, letting each idea arrive like moonlight easing through a window. Think of time not as a stern ruler, but as a soft current you're already resting in. With every slow breath, seconds turn to ripples, and the universe hums its low, steady lullaby. We'll visit the strange places where clocks disagree, where gravity tugs on moments, where motion stretches minutes thin, and we'll do it without strain, like watching stars drift past on a calm night. If this brings you peace, if science, whispered softly, helps you sleep, feel free to tap like or subscribe so we can meet here again, unhurried, whenever you need the dark to feel gentle. Now, nestle in. Let your shoulders fall. Let the day loosen its grip. We're not chasing answers. We're gliding toward them. Time will be kind tonight, and you can drift with it. What is time, really? It feels so familiar that we rarely stop to question it. We sense it everywhere, in the slow brightening of dawn, in the rhythm of our breathing, in the quiet turning of seasons that carry us forward. We see it in the way shadows stretch across the floor as the sun moves through the sky, and we hear it in the gentle ticking that marks the passage of moments we can never reclaim. Time seems so natural, so steady, that it becomes invisible, a silent companion that guides everything we do. Yet, when we begin to look closely, that simple, steady rhythm turns into something far stranger. For much of human history, time was thought to be absolute, a smooth river, flowing the same for everyone, everywhere. Ancient Egyptians carved their hours into stone by following the sun's shadow across tall gnomons, while Babylonians divided their days into neat patterns of 60, leaving behind the minutes and seconds that still define our clocks. In medieval towns, heavy mechanical clocks began to strike from the towers, their chimes echoing through the night, giving the impression that time could be measured, controlled, trusted. It felt like a great cosmic heartbeat, steady and impartial, untouched by where you stood or how fast you moved. Isaac Newton turned that sense into theory. In his vision, time was an invisible stage on which all events unfolded, a backdrop that existed independently of the universe it hosted. It ticked forward at the same pace for every star, every atom, every thought. This idea of time as universal and unchanging became the foundation of classical physics. For centuries, no one had reason to doubt it. The world seemed to obey that rhythm perfectly. The rise and fall of the planets, the pendulum swing, the orbit of the moon, all danced to a single cosmic beat. But the dawn of the 20th century brought a quiet revolution. In a time when science was already unraveling mysteries of light and motion, a young patent clerk named Albert Einstein began to question what everyone else took for granted. He asked, what if time itself was not separate from space? What if the two were woven together, like threads in the same tapestry? And what if the way time flows depends not on some universal clock, but on how we move, where we are, and what surrounds us? Einstein's theory of relativity turned that question into one of the most profound discoveries in science. He showed that space and time are inseparable, not two things, but one. A four-dimensional fabric called space-time. The universe is not built upon time. It is time and space woven together, bending and stretching as matter and energy move through it. In this fabric, The ticking of time depends on speed and gravity. Clocks do not agree because they are not measuring something fixed. They are measuring a living, flexible dimension that responds to the presence of everything within it. To understand this, imagine two travelers. One sits quietly at home, while the other races through space at nearly the speed of light. When they reunite, they will not have aged the same. The traveler who moved so quickly will have experienced fewer seconds, their clock having ticked more slowly. This isn't an illusion. It's a fact written into the structure of reality. Time itself has stretched for one observer and not for the other. It means that motion doesn't just carry us through space, it changes how we move through time. This phenomenon, known as time dilation, has been tested again and again. High above us, in the thin air where cosmic rays strike Earth's atmosphere, tiny particles called muons are born. They exist for only a heartbeat before decaying. By classical time, they should vanish long before reaching the ground. Yet they do, because they are moving so fast that their inner clocks run slower relative to ours. For them, more time passes before they fade. In the lab, scientists have sent precise atomic clocks aboard airplanes and satellites, comparing them with identical clocks kept still on the ground. When brought back together, the moving clocks always show that less time has passed. The difference is tiny, but measurable, proving that Einstein's vision was right. The faster you move, the slower time flows for you. Gravity, too, shapes time's rhythm. Einstein's general theory of relativity expanded the idea even further, showing that mass and energy do not merely exist in space-time, they warp it. Imagine placing a heavy sphere on a stretched sheet of fabric. The surface bends inward around it. Now imagine that fabric is space-time itself, and the bending changes how time moves. In stronger gravity, closer to the source of that mass, time slows. A clock at sea level ticks just a little slower than one on a mountaintop. Though imperceptible in daily life, this effect grows dramatic near massive objects like neutron stars or black holes, where space-time curves so deeply that an outside observer might see time nearly freeze at the edge, the event horizon. These ideas might sound like something out of dreams, yet they are woven into the technology that guides our waking lives. The satellites that form the global positioning system circle high above Earth, where gravity is weaker and motion is faster. Their clocks tick differently than those on the ground. Without adjusting for relativity for both motion and gravity, GPS would drift and fail within minutes. Every time you check your location on a phone, you are relying on Einstein's equations to keep your place in time. What this means is profound. There is no single cosmic rhythm, no universal now. Each observer carries their own clock, their own tempo of existence. Two events that happen simultaneously for one person might unfold at different times for another moving elsewhere. The idea that everyone shares the same present moment, that the universe is marching in step, is only an illusion born from our narrow human perspective. Yet, for most of us, living on Earth and moving at gentle speeds, these differences are so slight that time seems unified. A person walking down the street experiences almost exactly the same time as someone standing still beside them. But stretch that picture to the scale of galaxies, where space bends and velocities soar, and time becomes more fluid, more personal. Astronauts aboard the International Space Station orbit at about 7.7 kilometers per second, fast enough that their internal clocks tick a little slower than ours. Over 6 months, the difference amounts to less than a second. But it's real, a small echo of the vast machinery that governs all time. When we learn that time is relative, our sense of it begins to soften. The rigid walls between past, present, and future start to blur. We realize that the flow of time may not be a river outside us, but the way we experience change. In the language of physics, time is not simply the ticking of a clock, it is the ordering of events. What happens first? What follows? And by how much? But in the language of the heart, time is something we feel, a pulse that moves through memory and anticipation, through longing and rest. Even as modern science maps the geometry of space-time with exquisite precision, one mystery remains untouched. Why time exists at all? Why should reality have this direction, this arrow that points from before to after? The equations that describe the universe work just as well forward or backward. The stars don't care which way time moves, yet we do. We remember the past, but not the future. We see eggs break, but never unbreak. Somewhere in that asymmetry lies the secret of why we feel time's passage. Perhaps, as some physicists suggest, time doesn't truly flow. Maybe all moments past, present, and future exist together in a vast cosmic block, and consciousness merely moves across it like a traveler walking through a landscape of memories. Or perhaps the flow of time is a kind of illusion, an emergent rhythm born from deeper laws we have not yet discovered. Whatever the truth, time remains both intimate and unreachable, the closest thing we know, and the hardest to define. As you sit here, listening, breathing softly, you are part of that great mystery. Every heartbeat carries you a little farther along your personal timeline. You are traveling through the universe, not across space, but through time itself. Somewhere out there, beyond a faint shimmer of stars, there are worlds where seconds stretch longer, where gravity holds them still, and others where moments race past like light through glass. All of them are part of the same grand fabric, stitched together by motion, energy, and wonder. So when you close your eyes tonight and feel the hush between one breath and the next, remember that you are moving through something vast and beautiful. Time is not a prison, nor a rule to obey. It is the gentle current that carries every atom, every thought, every dream forward. You don't have to chase it or understand it completely. You only have to drift with it, softly, peacefully, as the universe keeps its quiet rhythm. The same rhythm that has been playing since the first light began to shine. At the dawn of the 20th century, physics seemed complete. Newton's laws had guided humanity for over 200 years, explaining everything, from the fall of apples to the dance of planets. Space appeared to be a fixed, silent stage, and time a steady river carrying every event forward. Together they formed the unshakable backdrop of reality, absolute, eternal, untouched by motion or matter. But small cracks began to form in that certainty. They appeared in the strange behavior of light, in the hidden puzzles of electromagnetism. Scientists had long believed that motion could always be measured relative to something, a great cosmic reference frame, a universal zero. Sound had the air, water carried waves, so it seemed only natural to imagine an invisible medium for light, the luminiferous ether. This ether, they thought, filled all of space, letting light ripple through it, as sound ripples through air. In 1887, two physicists, Albert Michelson and Edward Morley, tried to detect this ether. They designed an experiment so precise It could sense the Earth's motion through that invisible ocean. But no matter how they turned their instruments, the result was always the same. Light's speed never changed. Whether Earth moved toward or away from its supposed medium, the numbers refused to shift. It was as if the universe was whispering a quiet no to one of science's oldest assumptions. This result unsettled the scientific world. How could light disobey the rules that every other wave followed? If you run toward a sound, the waves reach you faster. If you run away, they slow down. Why should light be any different? Some proposed awkward fixes, perhaps objects moving through the ether shrank in the direction of motion, or perhaps our instruments subtly changed without us noticing, but none of it truly made sense. What if? Some wondered. The problem wasn't with the experiment, but with the way we understood space and time themselves. Into that moment of uncertainty stepped a young man who worked in a patent office, Albert Einstein. In 1905, at the age of 26, he published a paper that would change everything on the electrodynamics of moving bodies. In it, he proposed two simple principles that would quietly rebuild the universe from the ground up. First, the laws of physics are the same for all observers moving at constant speeds relative to one another. Second, the speed of light in a vacuum is constant for everyone, regardless of how they move or where they are. At first, these ideas seemed harmless, even obvious, but together they demanded a revolution. If light's speed is the same for everyone, then space and time cannot remain fixed. They must bend, stretch, and adjust to keep light's rhythm constant. Time must slow for those in motion. Distances must contract. Even the idea of simultaneity of two things happening at the same time must depend on who is watching. Imagine a train gliding down the tracks. A flash of light goes off in its center. To the passenger on the train, the light reaches the front and back at the same moment. But to the observer standing on the platform, the train's rear is moving toward the flash, while the front moves away. If the speed of light is the same for both, then they cannot agree on which end the light reached first. For one, the two events are simultaneous. For the other, they are not. Each is correct within their own frame. Time itself, the order of before and after, has become relative. This realization shattered the old illusion of universal time. A moving clock, Einstein showed, runs slower compared to one at rest. A ruler in motion shortens along its direction of travel. These effects are not tricks of perception, but genuine features of the universe. At everyday speeds, the difference is tiny, too small to notice. But as motion approaches the speed of light, time stretches dramatically. Were you able to travel that fast? Your seconds would slow to stillness, while the rest of the universe raced ahead. Einstein's insight also explained the Michelson-Morley puzzle. There was no ether, no invisible sea. Light didn't need a medium at all. It simply followed the geometry of space-time. Its constancy wasn't a mystery, it was a clue to how reality itself was built. Space and time were not separate backdrops, but part of a single, flexible fabric that could bend and twist to preserve nature's deepest symmetries. Relativity wasn't just a beautiful idea, it made predictions that could be tested. And over the years, those tests came quiet, precise, and undeniable. Particles called muons, created high in Earth's atmosphere, live longer when moving near light speed because their internal clocks tick slower. Atomic clocks flown on jets and satellites have been compared to those kept on the ground, showing the same effect. The faster they move, the slower they run. Every experiment has agreed with Einstein's math, confirming that motion truly shapes time. The theory that began as a thought experiment now underpins our modern world. The GPS satellites orbiting high above Earth rely on it to keep time precisely. They move fast, where gravity is weaker, and both factors alter how their clocks tick. Without corrections based on relativity, GPS would drift by kilometers each day. Each time you navigate to a cafe or find your way home, Einstein's equations are quietly guiding you there. But special relativity was only the beginning. It dealt with motion at steady speeds, where acceleration and gravity were ignored. Einstein soon realized that acceleration and gravity could be understood as the same thing, both effects of space-time's curvature. In 1915, he expanded his theory into what we now call general relativity. In this broader view, gravity is not a force pulling objects downward. It is the bending of space-time itself around mass and energy. Time slows near massive bodies, faster, farther away, near something like a black hole. That slowing becomes almost infinite seconds, stretching into eternities. Even stripped of gravity's complexity, Einstein's special relativity changed everything we thought we knew about time. For centuries, people imagined a single cosmic clock ticking in perfect unison across the universe. But Einstein showed there is no such clock. Each observer, each particle, each star carries its own rhythm. The laws of physics care not about one universal time, but about how these individual rhythms relate to one another. Time is not a background. It is part of the fabric, woven from motion, matter, and energy. This idea is unsettling, yet deeply poetic. It means the universe has no single now. The present moment is local, personal, tied to your own motion and position. Two distant events that seem simultaneous to you may not be so for someone else. Time is like a vast ocean filled with countless ripples, each belonging to its own traveler. And yet, these ripples interweave perfectly, forming one continuous whole. Each of us carries our own current, but together they form the sea of space-time. Over the past century, relativity has been tested more thoroughly than almost any other theory in science. It guides spacecraft across the solar system, explains the bending of starlight around the sun, and allows physicists to predict how matter behaves in the hearts of galaxies. Every observation, from the ticking of atomic clocks to the signals from distant pulsars, has confirmed its truth, and still, its central insight remains as haunting as ever. Time is not absolute. It is elastic, responsive, alive. There's something quietly human in that realization. We live as though we share one universal timeline, one great flow that carries us all. But in truth, each of us moves through time at our own pace. No two journeys are identical. Somewhere in the cosmos, another clock is already ahead of yours. Somewhere else, one lags behind. None is more real than the other. The universe allows each to keep its rhythm and still remain part of a single harmony. Perhaps that is Einstein's most beautiful gift, not just the equations that describe space-time, but the humility they teach. They remind us that what feels solid and simple may only be a small slice of something far more intricate. Time does not belong to one observer or one point of view. It belongs to the relationship between them, to the dance that binds every traveler in the cosmos. So tonight, as you listen and breathe, imagine yourself on that quiet train again. Outside the window, the world drifts by. Inside, a soft light flickers and fades. Somewhere far away, another traveler sees it differently, their seconds unfolding in a gentler rhythm. Both are true. Both belong. And in that shared yet separate journey, you can feel what Einstein revealed, that time is not a single ticking clock, but a living, shifting fabric, carrying us all through the silent glow of the universe. In daily life, time feels steady, a quiet rhythm that never stumbles. You wake, walk, speak, breathe, and every second seems to slip by at the same pace for everyone around you. The clock on your wrist agrees with the one on the wall. Trains arrive on time, and your heartbeat keeps its gentle cadence. For centuries, this smooth, shared flow has shaped how we think about time itself. Yet, physics reveals a deeper truth. Time does not move the same way for everyone. Its flow depends on how you move through space and through the fabric of space-time that holds everything together. Einstein's theory of relativity tells us that space and time are not separate things, but two faces of a single fabric. Space-time, every object, from a drifting grain of dust to a swirling galaxy, traces a path through this fabric, called a world line. The rate at which something moves through time depends on how much of its total motion is spent moving through space. When you are still, nearly all your motion is through time. As you move faster, more of your journey tilts towards space, and less of it passes through time. It's not something you can feel. Even if you traveled through the cosmos at near the speed of light, your own clock would feel normal. Your pulse, your thoughts, the pace of your speech, everything would unfold just as it does now. But for someone watching you from Earth, your seconds would stretch. Your heartbeat would appear slower, your movements softer, your entire life unfolding in slow motion. And from your perspective aboard that ship, the same would be true of the people on Earth. Both viewpoints are correct. And that symmetry lies at the heart of special relativity. There is no universal timekeeper to declare who is right. Time depends on relative motion. It bends to the path each traveler takes. The famous twin paradox captures this perfectly. Imagine two identical twins. One remains on Earth, the other journeys to a distant star and back at near light speed. When they reunite, the traveling twin has aged less than the one who stayed behind. The difference isn't an illusion or a trick of biology. It's a result of motion itself, of how each twin's world line carved through space-time. The one who traveled farther through space moved more slowly through time. This strange truth is not limited to imagination. It has been proven many times. High in Earth's atmosphere, particles called muons are born when cosmic rays strike air molecules. At rest, muons last only about 2 millionths of a second, far too brief to reach the ground. Yet they do, because they are moving so fast that, from our perspective, their internal clocks slow down. Their short lifetimes stretch long enough for them to reach detectors on Earth. In laboratories, scientists have confirmed this with beams of muons in particle accelerators. The faster they move, the longer they live. Every result matches Einstein's prediction with perfect precision. The same effect has been measured with clocks, the most faithful companions of time itself. In the 1,970 seconds, scientists flew atomic clocks on commercial jets while keeping identical clocks in laboratories on the ground. When compared afterward, The flying clocks showed that slightly less time had passed for them. The difference was tiny billionths of a second, yet entirely real. Today, these same principles guide the global positioning system orbiting above us. Each GPS satellite carries an atomic clock moving thousands of kilometers per hour relative to Earth. Because of their motion, the satellite's clocks tick a little slower, but they also orbit higher, where gravity is weaker, and that makes their clocks tick faster. Engineers must correct for both effects. Without those adjustments, GPS signals would drift by kilometers each day. Every map we open, every location we find, works only because Einstein was right. So time dilation, the stretching and slowing of time, is not a curiosity. It is the rhythm of the universe. When you move quickly relative to someone else, your flow of time truly changes. The difference is imperceptible at walking speeds, almost non-existent even in an airplane. But as you approach the cosmic speed limit, the speed of light, the change grows dramatic. At 99% of light speed, time for you would pass at less than half the rate of someone standing still. Push closer to that limit, and your seconds would stretch into hours, days, or even years compared to theirs. At such speeds, the laws of nature offer a form of time travel. Not backward, but forward. You could journey to a distant star in what feels like a few years to you, only to find that centuries have passed back on Earth. Countless stories have been inspired by this idea. Travelers who return to find their home world changed beyond recognition, left behind by time itself. It sounds like fiction, but it's built into the mathematics of relativity. The faster you move, the slower your personal time flows. Motion through space becomes a quiet exchange for motion through time. Yet this slowing does not distort your experience. To you, time remains smooth and natural. Your body, your thoughts, your heartbeat, all continue as normal. It's only when compared to another observer's timeline that the difference becomes visible. That's what makes relativity so counterintuitive. Each person experiences their own now, their own private flow of time, shaped by their unique motion through space-time. When two travelers finally meet again, their clocks tell slightly different stories, both true, both reflections of the paths they've taken. This connection between space and time runs deep. Everything that exists moves through space-time at the same total speed, the speed of light. When you are still, you move through time at that full rate. When you move through space, some of that motion is spent sideways across the spatial dimensions, and your passage through time slows. A beam of light spends all its motion on space and none on time. From its perspective, if one could imagine such a thing, the moment it is emitted and the moment it is absorbed happen together, with no time in between. That is the ultimate limit. Light does not age. For everything else, time flows according to motion. Even satellites, astronauts, and planets feel it. Astronauts aboard the International Space Station orbit Earth at over 7.7 kilometers per second. Because of that speed, they experience time slightly more slowly than people on the ground, though the weaker gravity above them slightly offsets it. After 6 months in orbit, the difference is less than a second. Tiny, yes, but enough to prove that no two clocks in the universe ever tick in perfect unison. Time dilation has become one of the most precisely measured effects in physics, tested in every context, from particle accelerators to planetary orbits. The results are always the same. Motion and gravity shape the rhythm of time. It is not something we can escape or override. It is built into the geometry of the universe itself, into the way space-time folds and stretches around mass, energy, and speed. If you could travel near the speed of light, you would carry your own rhythm into the future. For you, years might pass softly, while decades unfold elsewhere. You could cross the galaxy and return to a home unrecognizable. The oceans changed. The constellations shifted. The voices of history, long silent. To the universe, nothing paradoxical has happened. You simply took a different path through the same fabric of space-time. Even without rockets or relativity, the lesson touches us all. Each of us is already a traveler through time, moving at our own pace. The differences are too small to notice, yet they exist between the watch in your hand and the clock on a mountain, between an airplane above and the city below. Time's rhythm is not uniform. It is a harmony of countless subtle tempos. The cosmos keeps perfect order, not by forcing sameness, but by allowing every path to carry its own beat. Relativity, then, is not just a scientific theory. It's a reminder of perspective. It tells us that time is personal, local, alive, that there is no single now for all of creation. The present moment is not a universal stage where everyone stands together. It is a moving spotlight that follows each traveler through their journey. Sometimes those spotlights cross, and we share a moment. Then they drift apart again, carrying their own rhythm forward through the infinite sea of space-time. When you pause to listen to your heartbeat or watch the shadows shift on a wall, you are measuring your own private time. Somewhere else, someone's seconds are flowing a little faster or slower, their clocks marking a different rhythm. Both are true, both connected, both part of the same great pattern. So the next time you glance at a clock, imagine the invisible dance behind its ticking, the way motion and gravity shape every second that passes. You are not standing still. You are moving through time and space, tracing your world line through the quiet architecture of the cosmos. Every breath, every step, every heartbeat is part of that motion. In this way, relativity becomes more than a theory about light or speed. It becomes a meditation on existence. Time is not something outside of us, but something we carry. Something that bends gently to the way we move. The universe does not offer one rhythm for all, but countless melodies woven together into one vast, harmonious flow. You are a part of that music, a traveler through space-time, moving always forward, always changing, yet never alone. And even though our clocks may never agree, they all belong to the same silent song the universe has been humming since the first light began to shine. It feels natural to think of gravity as a pull, a quiet, constant hand drawing everything downward. You drop an apple and it falls to the ground. Let go of a stone and it sinks toward the pond with soft inevitability. This is the gravity of everyday life, familiar, invisible, dependable. It keeps our feet on the ground and our world in place. For centuries, that simple image guided our understanding of the universe. Isaac Newton described gravity as an attraction between any two masses, acting across the emptiness of space. It was an elegant law, strong enough to predict the orbits of planets and the return of comets with breathtaking precision. Yet, in Newton's universe, gravity and time were separate things. No matter how strong the pull, Time ticked on at the same steady pace everywhere. Then came Einstein. In 1915, he offered a new vision, a universe not ruled by invisible forces, but shaped by geometry. In his general theory of relativity, gravity is not a force at all, but the bending of space-time itself. Massive objects like planets, stars, and black holes curve the fabric of space-time around them. Other objects, and even light, move along the curves of this fabric. To fall toward Earth is simply to follow the path that space-time itself has drawn. The apple's descent is not a pull downward, but a glide through a warped landscape. And that landscape affects more than motion, it affects time. Where gravity is stronger, time runs slower. The closer you are to a massive object, the more space-time curves, and the more that curve stretches time's rhythm. This slowing of time isn't an illusion, nor is it caused by stress or strain. It is a built-in feature of reality, a direct consequence of how space-time bends around mass and energy. To picture it, imagine space-time as a vast, flexible sheet. A planet like Earth creates a shallow dent, a star, a deeper well, a black hole, a bottomless pit. Clocks placed at different depths in this curvature tick at different speeds. The deeper you go, the slower your clock runs. This is gravitational time dilation, one of Einstein's most beautiful and counterintuitive discoveries. On Earth, the effect is tiny but measurable. A clock at sea level ticks ever so slightly slower than one on a mountain peak. The difference is only billionths of a second per day. But atomic clocks are sensitive enough to reveal it. In a 2010 experiment, scientists placed two identical clocks, just 33 centimeters apart, one on the floor, the other on a high shelf. The lower clock, closer to the center of Earth's gravity, ticked more slowly, exactly as Einstein predicted. The difference was only a few parts in 100 trillion, yet real and consistent, a faint echo of the universe's geometry. The same principle extends into space. Satellites orbiting high above Earth experience weaker gravity, so their clocks tick faster than those on the ground. At the same time, the rapid motion causes a special relativistic slowing of time. Engineers must account for both effects to keep our GPS system accurate. Without those corrections, navigational errors would build up at a rate of nearly 10 kilometers per day. Each time your phone guides you home, it is quietly confirming that time bends under gravity's hand. But near truly massive objects, this gentle bending becomes astonishing. Consider a neutron star, the collapsed heart of a once mighty sun. Its mass exceeds that of our own star, yet it is only about 20 kilometers wide. The gravity at its surface is billions of times stronger than Earth's. A clock resting there would tick unimaginably slowly compared to one far away in open space. From a distance, every process on that star, the cooling of its crust, the flicker of its magnetic field would appear to unfold in slow motion. And deeper still lies the black hole gravity at its most extreme. Here, mass is crushed into a point of infinite density, wrapped in an invisible boundary known as the event horizon. Nothing, not even light, can escape once it crosses that threshold. As you approach the horizon from afar, time begins to stretch alarmingly. Your clock ticks slower and slower. From the viewpoint of someone watching from a safe distance, you never quite reach the horizon at all. Your movements appear to freeze, suspended forever in the last instant. before falling away. Even the light coming from you changes. As you draw nearer to the event horizon, it is pulled and stretched by the gravity you're sinking into. Its color shifts toward red, then fades to black as the wavelengths grow longer and longer, a final whisper of your presence sliding out of view. Yet, from your own perspective, nothing unusual happens. You drift inward, your heartbeat steady, your seconds unfolding normally. The strange truth is that while time slows for you relative to the outside universe, it still feels the same within your own frame of reference. You would pass the event horizon without noticing, even as the rest of the cosmos races ahead by millions or billions of years. Astronomers have seen the signature of this effect in real light from real matter. Around black holes, gas spirals inward in a glowing ring called an accretion disk. As it plunges deeper into gravity's well, its light becomes redshifted, stretched to longer wavelengths, showing that time there moves differently than it does in the emptier regions of space. These measurements match Einstein's predictions perfectly. The bending of light, the slowing of time, the dance of gravity all unfold exactly as his equations describe. The lesson reaches far beyond black holes. Gravitational time dilation happens everywhere, from the depths of galaxies to the curve beneath your feet. Wherever there is mass, space-time bends. Wherever space-time bends, time slows. The same equations that describe the arc of a planet's orbit also describe the way seconds stretch in the presence of gravity. It's a single story told in two languages, motion and time, though we cannot feel it. Gravity is quietly reshaping the pace of our lives. A person at sea level ages a tiny bit slower than someone on a mountain. A pilot flying high above the clouds experiences a slightly faster flow of time than the people waiting below. The effect is imperceptible, but constant. It means that time, even here on Earth, is not perfectly uniform. It is sculpted by the planet's mass and our position within its embrace. In more extreme environments, these small differences grow vast. A person living near the surface of a neutron star, if they could somehow survive its crushing gravity, would experience only hours, while centuries passed elsewhere. In that sense, gravity offers another path to the future. Just as high-speed motion slows time, so too does deep gravity. A traveler could, in theory, spend a short time near a massive object and emerge to find that ages have passed for everyone else. Science fiction dreams of journeys to the future through acceleration. Relativity allows the same through gravity. Of course, the reality is far less forgiving. The regions where gravity slows time most dramatically are also places of unimaginable danger, crushing densities, lethal radiation, space itself curved into near collapse. Yet the principle holds true everywhere. Gravity and time are partners, inseparable, each shaping the other. This understanding dissolves the illusion of a universal now. The universe does not tick in unison. Every planet, every star, every point in space has its own local rhythm, its own tempo shaped by gravity and motion. Time in the deep heart of a galaxy moves differently than time between its spiraling arms. Even within your own body, your head is aging a few trillionths of a second faster each year than your feet. The cosmos is not a single clock, but a chorus, a web of countless rhythms woven together by space-time's geometry. To grasp this is to glimpse something quietly profound. The gravity that keeps your feet on the ground is the same gravity that stretches the seconds between pulses of a distant star. It is not a separate force, acting on time. It is time's very shape. The pull you feel is the curvature of the fabric that defines your existence. And though you can't feel your seconds bending, they are slightly slower in valleys, slightly faster on peaks, each place carrying its own tempo within the symphony of the universe. When we look out at the night sky, the light that reaches us has already been delayed, stretched, and aged by the gravity it has passed through. Every star, every galaxy, every glowing filament of the cosmos is sending us not only its light, but its version of time. The universe we see is layered, not just in space, but in time itself. In the end, Einstein's insight turned gravity from a simple pull into a story of connection, a reminder that time is not fixed, but living, molded by mass and energy. Each of us moves through our own gentle curve of space-time, flowing through a private river of seconds. Two people standing side by side are almost perfectly synchronized, yet never exactly, and somewhere far away, near a black hole's edge, another river flows so slowly that our entire civilization could rise and vanish before one of its minutes has passed. All of these rivers, fast, slow, deep, and shallow, merge into the same vast ocean of space-time. There is no master current, no universal tide, only countless streams flowing together, bending and weaving through gravity's invisible architecture. Time does not rule over gravity. Gravity is time, shaped into form, and within that quiet truth lies something deeply human, the knowledge that every breath, every heartbeat, every falling apple is not only moving through space, but through time itself, guided by the same cosmic curve that holds the stars in their endless orbits. For most of us, time dilation feels like a distant curiosity, something that happens only near black holes or in high-energy physics labs. But the truth is far more intimate. Time dilation quietly runs beneath the surface of daily life, hidden inside the systems that guide, connect, and protect us. Without the subtle corrections of relativity, our world would quickly drift out of sync. The clearest example lives above our heads. The Global Positioning System, GPS, is a constellation of satellites orbiting about 20,000 kilometers above Earth, each carrying atomic clocks of extraordinary precision. These clocks broadcast timestamps and orbital data toward Earth. On the ground, your receiver in your phone, car, or ship compares the arrival times of signals from at least 4 satellites. Since light travels at a fixed speed, the receiver calculates how far each signal has traveled and triangulates your exact position. This process depends entirely on perfect timing. A clock error of just a few billionths of a second can shift your position by several meters. A drift of microseconds would send your map sliding kilometers away from reality. Synchronization between satellite and ground clocks is essential, yet relativity makes that synchronization impossible without correction. The satellites move fast, about 14,000 kilometers per hour, and according to Einstein's special relativity, moving clocks tick more slowly. This motion makes the onboard clocks lose about 7 microseconds per day compared to clocks on Earth. But the satellites also orbit higher. Where Earth's gravity is weaker, general relativity tells us that clocks in weaker gravity tick faster. And this effect adds about 45 microseconds per day. Combined, the net difference is roughly 38 microseconds daily. That may sound small, but light travels about 11 kilometers in that time. Without correction, GPS would drift by nearly 10 kilometers each day, useless for navigation. Engineers fix this by offsetting the satellite clocks before launch so that once they're in orbit, their tick rate naturally matches Earth's. Ground stations constantly monitor and fine-tune those frequencies, compensating for orbital shifts and temperature effects. Every time your phone finds your location, it is quietly solving Einstein's equations. GPS is just the most visible place where relativity keeps order. The same principles pulse through the veins of our global communication networks. Fiber optic cables, microwave towers, and satellites move data in tightly timed sequences. When two signals arrive slightly out of order, packets can be lost or corrupted. To keep the entire web synchronized, network engineers rely on clocks that exchange timing signals across vast distances, and every link must account for relativistic effects. Even finance depends on Einstein. High-frequency trading systems timestamp transactions to the billionth of a second, determining who bought or sold first across servers thousands of kilometers apart. These networks use atomic clocks and satellite time signals corrected for motion, altitude, and gravity. A tiny, unaccounted lag could reorder trades, shifting money by millions. The precision that keeps global markets fair and accountable is the same precision that governs space-time itself. In the science of measurement, metrology relativity is a daily companion. National laboratories around the world maintain atomic clocks to define the second and keep global time unified. When these clocks are compared across continents, even their tiny differences in altitude matter. A clock on a mountain ticks faster than one at sea level, and both differ slightly from clocks in orbit. Scientists correct for these differences to maintain coordinated universal time. The heartbeat of our technological civilization, as clocks become ever more precise. Even small changes in height can alter their tick. In 2010, researchers placed two identical atomic clocks, only 33 centimeters apart, and found that the lower one, sitting deeper in Earth's gravity, ran slower, just as general relativity predicts. It's an almost poetic reminder that gravity's hand touches everything, even the space between a tabletop and a shelf. Time dilation also guides our exploration of the cosmos. When signals travel to and from deep space probes, engineers must account for the craft's velocity and position in the sun's gravitational field. A delay of just microseconds can alter navigation by thousands of kilometers. The faint radio pulses that reach Earth from Voyager or New Horizons carry traces of these relativistic shifts. Correcting for them allows us to track each craft with exquisite precision, even at the edge of the solar system. Astronomy, too, listens through the lens of time. Pulsars, spinning neutron stars that flash regular radio pulses, serve as natural clocks, but their light travels through curved space-time, distorted by the gravity of stars and galaxies. Astronomers must correct for these delays to measure positions and distances accurately. Relativity is written into every equation that translates a cosmic signal into knowledge. In particle physics, time dilation becomes impossible to ignore. Inside accelerators like CERN's Large Hadron Collider, particles race around rings at nearly the speed of light. Unstable particles that should decay almost instantly live much longer in motion. Their internal clocks slowed relative to the lab. Experiments depend on these stretched lifetimes to observe their properties. Every successful measurement confirms, again and again, that time truly changes with speed. Even the infrastructure of everyday life rests on this subtle elasticity of time. Electrical power grids, for instance, rely on precise synchronization between generators spread across continents. Radio telescopes on opposite sides of Earth record signals from the same galaxy and later combine their data to form a single, sharp image. For the timing to align, engineers must factor in both Earth's rotation and the tiny relativistic shifts in the clocks used. Without these corrections, the signals would blur into noise. We rarely think about these layers of physics woven into modern systems, yet they hold our civilization together. Each moment your phone refreshes a map. Each instant, a plane navigates through clouds or a ship crosses the sea. Einstein's equations are running quietly in the background, transforming abstract theory into the rhythm of daily life. It is humbling to realize that the same laws that shape black holes also guide your morning commute. Newton imagined a universal time flowing evenly for all, a stage upon which the universe's events unfold. But in our world, the world of satellites, data networks, and precise clocks we live by, Einstein's vision, time is local, elastic, and deeply intertwined with motion and gravity. Every system we build must bow to that truth. Without relativistic corrections, our navigation would fail, our networks would desynchronize, and even our definitions of seconds and meters would drift apart. The world appears synchronized only because we have built it to compensate for nature's quiet asymmetries. There's a kind of beauty in this invisible coordination, billions of devices, each with its own imperfect heartbeat, united through physics into one shared rhythm. Every GPS signal, every trading timestamp, every synchronized network frame is an echo of space-time itself. Finding harmony. When you glance at your phone's map, you're not just seeing your position on Earth, you're seeing the outcome of atomic clocks orbiting above you, all ticking at slightly different speeds, all adjusted by Einstein's equations so your world can stay coherent. You're participating in a small act of cosmic balance, proof that understanding how time bends and stretches allows us to live within its flow rather than be lost in it. Relativity, once a theory whispered in the language of geometry, now lives inside your pocket. It guides airplanes through storm clouds, lets surgeons synchronize robotic instruments, allows astronomers to watch galaxies form across billions of light years. It ensures that the signals of our civilization, from heartbeats to data streams, move together through the subtle curvature of space-time. Beneath every screen, tap, and satellite ping lies the same message. Time is not absolute. Each clock in orbit, in a lab, or in your hand keeps its own unique tempo, shaped by motion and gravity. Our technology forces those tempos into harmony, weaving a tapestry of countless local times into one global rhythm. The next time your navigation marker flickers on a glowing map, pause for a moment. Behind that simple signal, dozens of satellites are whispering through the dark, their clocks offset and corrected by the bending of space-time. Engineers on Earth, listen, align and adjust, keeping your steps in sync with the geometry of the cosmos. Einstein's discovery was not just about distant stars or speeding particles, it was about us. Every second of modern life depends on the quiet truth that time flows differently for everyone, everywhere. And yet we can still find connection within that difference. So when you look at your phone, your watch, or the night sky, remember, you are not just measuring time, you are living inside it, moving through a universe that bends gently beneath your feet. The same equations that shape galaxies also keep you on the right road home. Across most of the universe, time moves in a calm, steady rhythm. On the surface of a moon, drifting between stars, or circling a planet, seconds pass almost evenly, too smoothly or our senses to tell the difference. But hidden within this cosmic quiet are places where that rhythm breaks, where time slows to almost nothing. These are the deepest wells of gravity, the regions where space bends so steeply that even light struggles to climb free. And in those silent depths lies the slowest time in the universe, the edge of a black hole. A black hole is gravity in its purest form. It begins when a massive star runs out of fuel, collapses inward, and compresses its mass beyond the point of resistance. What remains is a region so dense that it warps space-time into a pit with no bottom. At the center is a singularity, a point where our physics falters. Surrounding it is the event horizon, not a surface you can touch, but a boundary where escape velocity equals the speed of light. Beyond that invisible veil, no light or signal can return. From a distance, a black hole can seem deceptively calm. If you orbited one safely, the experience might feel like circling any other massive object. But the closer you drift, the more space and time twist together. Gravity grows stronger. The curvature of space-time deepens, and the passage of time begins to warp. Imagine lowering a clock toward the black hole while you stay far away, watching through a telescope. At first, the clock ticks normally, but as it sinks, its rhythm slows. The light it sends toward you shifts red, stretched by gravity itself. Each second on the falling clock takes longer to reach your eyes. As it nears the event horizon, the clock seems to crawl. Finally, just before it reaches the boundary, it appears to stop completely frozen in place, its final tick suspended forever. This isn't an illusion. It's a direct consequence of how gravity shapes time. From your perspective, it would take an infinite amount of time for the clock to actually cross the event horizon. Nothing seems to fall in. But for the clock or an astronaut falling beside it, time flows normally. Seconds pass as always. They would feel no sudden pause or resistance when crossing the horizon. The contradiction exists only between viewpoints. To you, they slow and fade. To them, time continues in its quiet rhythm. This is relativity at its most dramatic. Two realities existing at once, both correct. The closer you move toward the singularity, the greater the stretch between these versions of time. In the deepest gravity wells, even the difference between your head and your feet can become enormous. For small black holes, that difference is violent. The pull at your feet could be so much stronger than at your head that your body would stretch and thin, a process grimly known as spaghettification. But for supermassive black holes millions of times heavier than the sun, the story changes. Their gravity is spread over a wider region, making the tidal forces near the event horizon gentle. You could, in theory, cross it unharmed. Yet, the difference in time between you and the rest of the universe would still be extreme. If you could hover just above that horizon, your clock would nearly stop compared to one floating far away. A few minutes for you might equal centuries out in the cosmos. The stars above would seem to move faster, galaxies drifting like quick clouds, the universe aging in fast motion while you hardly notice a thing. This isn't fantasy. Astronomers have seen traces of this slow time in the light surrounding black holes. Matter spiraling toward them forms glowing disks of gas and dust, heated to incredible temperatures before vanishing beyond the horizon. The light from that matter is stretched. Its color shifted to red, a sign that time near the black hole is crawling compared to ours. By measuring how much the light is redshifted, scientists can calculate the black hole's mass and even estimate how fast it spins. The idea that time could slow to a crawl has also captured the imagination of storytellers. In Interstellar, astronauts visit a planet orbiting close to a supermassive black hole, where an hour on the surface equals 7 years for those far away. While exaggerated, the principle is real. Strong gravity bends time so powerfully that a short stay near such a planet could let you return to a future centuries ahead. A black hole, in this way, becomes a one-way ticket to the far future, not through science fiction magic, but through Einstein's geometry of space-time. If you could orbit near a black hole's edge and then escape, you'd find that your personal clock had recorded far less time than the clocks of those waiting for you. Their world would have aged while yours seemed still. A few hours of your life could span entire eras in the universe beyond. Time travel, in this quiet sense, is already written into the structure of reality, but within the event horizon itself, time behaves differently again. Everything, light, matter, even space, flows inward, drawn toward the singularity, where the known laws of physics unravel. You wouldn't see the moment you cross the horizon. Nothing marks the boundary except what you can no longer escape. From the outside, you vanish slowly. From your own perspective, you fall swiftly, carrying your seconds with you into a region where time and space trade places. Even light feels this distortion. A photon that escapes from near the horizon loses energy as it climbs away, stretching into longer wavelengths. It becomes a redder, weaker echo of itself, a message from slower time. Each such photon carries the memory of the gravity it escaped, its fading color telling us how deeply time was slowed at its birthplace. This slowing of time isn't just theoretical. It shapes how black holes behave. It determines how fast they pull in matter, how they appear to observers, and even how they evaporate through Hawking radiation, the faint whisper of quantum energy that lets them lose mass over billions of years. All of these effects depend on the strange way time dilates in their presence. Near a black hole, every process is stretched, slowed, and softened by the curve of space-time. It's tempting to imagine what it would feel like to live near such a place. If you could somehow survive the gravity and radiation, you'd experience the universe speeding up around you. The stars would shift across the sky, constellations twisting into new shapes in hours or days. Galaxies might drift like clouds. Civilizations elsewhere could rise and vanish before your own heartbeat finishes its rhythm. For you, nothing would feel unusual, but the universe beyond would be racing ahead, leaving you anchored in slow time. This is the profound lesson of relativity. Time does not flow the same for everyone. It depends on where you stand in the landscape of space-time. The deeper the gravity, the slower the pace. The farther you climb from a massive object, the faster your seconds pass. There is no single universal now connecting the cosmos, only local rhythms, each one true in its own frame. And so, the slowest time in existence belongs to the very edge of black holes, the quiet rim where seconds stretch into eternity. To us, those places seem frozen, their light fading into red and then to black. But within them, time still flows for the falling traveler, unbroken and ordinary, even as the universe outside rushes ahead, beyond recognition. Perhaps the most astonishing truth is that these extreme places are not rare. Astronomers believe most galaxies, maybe all, hold a supermassive black hole at their center. Around them, time moves differently. Whole stars orbit within regions where clocks tick slower than our own. On a cosmic scale, the universe is filled with pockets of stretched time, places where the tempo of existence softens almost to silence. It changes how we think of our own brief lives. We measure time in heartbeats and seasons, believing it constant. But the cosmos holds countless clocks, each with its own rhythm, shaped by motion and gravity. Somewhere near a black hole, a single second lasts longer than all of human history, while light from that same region climbs slowly outward, whispering across eons. Time, we realize, is not a single river flowing evenly through the universe. It is a vast network of currents and eddies, each moving at its own pace. The black hole is simply the deepest of these. A whirlpool where the river almost stands still. And yet, even there, the story continues. The universe beyond the horizon keeps evolving, its galaxies spinning, its light traveling, its ages passing. The slowest clock in existence does not stop the dance of time, it only reminds us how varied that dance can be. So when you look up at the night sky, remember, some of those stars you see may be circling invisible giants, where seconds stretch into forever. Out there, in the most silent corners of space-time, time itself is falling softly, endlessly into the dark. Is time travel possible? The question has haunted storytellers and scientists alike for centuries, long before relativity or equations. Myths spoke of wanderers who stepped into enchanted realms and returned to find that years had passed in a single night. Today, the idea lives on in science fiction ships sailing through time, portals to the past, journeys to distant futures. But behind the wonder lies a real question of physics. Can time itself be navigated like space? In one quiet sense, we already do. Every heartbeat carries us forward through time at 1 second per second. We are all moving through the future, slowly, evenly, together. Einstein's theory of relativity only deepened this realization by showing that this rate is not fixed. Motion and gravity reshape time's flow, bending its steady rhythm. Move faster, or stand in stronger gravity, and your seconds stretch compared to someone else's. This isn't science fiction. It has been measured again and again in laboratories, satellites, subatomic particles, and even the signals that guide your phone's GPS. Time is elastic. The faster you travel, or the deeper you stand in a gravitational field, the slower your personal clock runs. When you return from your journey, the world you left behind will have moved ahead. In this way, relativity already grants us one-way time travel, not into the past, but into the future. If you could ride a ship near the speed of light, you might experience only a few years while centuries pass on Earth. Orbit close to a supermassive black hole. In an hour for you could equal decades elsewhere. The physics is exact, the effect real. Only the technology remains beyond our reach. Yet, even without such extremes, the principle stands. The universe lets you slide forward in time at different rates. But travel to the past, that's where the dream darkens. Relativity's equations do not forbid it entirely, but the paths that allow it are twisted and rare, demanding conditions far beyond anything we know how to build. In theory, some solutions to Einstein's equations create what physicists call closed time-like curves, loops through space-time that circle back on themselves. An object following such a path could, in principle, return to its own earlier moment. Among the most famous of these ideas is the wormhole, a hypothetical tunnel connecting two distant points in space-time. If such a bridge could exist, it might allow you to travel instantly from one mouth to the other, and if time passes differently at each end, then stepping through could carry you backward or forward in time, move one mouth quickly, or lower it into a strong gravitational field. And time would slow for that end, reunite them later, and they would no longer agree on what now means. Walk through, and you might emerge in an earlier era. The idea is elegant, but fraught with obstacles. For a wormhole to remain open, it would require exotic matter, material with negative energy density, something never observed in usable form. Quantum theory allows tiny flickers of such negative energy for brief moments. But whether it can be stabilized long enough to hold open a cosmic tunnel is unknown. Even if it were possible, the structure might be unstable, collapsing or releasing enormous radiation before anyone could pass through. Stephen Hawking once suggested that the universe itself may prevent such machines from existing. His chronology protection conjecture proposed that nature enforces consistency, flooding any would-be time loop with enough quantum energy to destroy it before paradoxes arise. No one has proven this law. But so far, the absence of tourists from the future suggests that if time machines are possible, they are either rare, hidden, or self-limiting. Other theoretical models, rotating universes, or massive spinning cylinders also allow closed time-like curves without exotic matter. In these, the rotation of space-time itself twists time into loops, yet these solutions require impossible conditions. Infinite cylinders, uniform density, or cosmic rotation on scales our universe simply doesn't exhibit. They are beautiful thought experiments, not blueprints, and even if a path backward could exist, deeper problems remain. Causality, the principle that cause precedes effect, would crumble. Could you meet your younger self? Change an event that led you to go back in the first place? The logic tangles quickly into paradox. Perhaps that's why some physicists turn to the idea of self-consistency, that if time travel to the past is possible, every action taken there was always part of history. You can visit, but you cannot change what has already been written. Others reach for quantum ideas to escape the knot. In the many worlds interpretation of quantum mechanics, every outcome of every event exists in its own branching universe. A trip into the past, in this view, might send you into a different branch, a nearby timeline where your choices diverge. You wouldn't alter your own history, but begin a new one. Elegant, perhaps, but still beyond experiment. These ideas live at the edge, where physics touches philosophy, where mathematics begins to sound like myth again. What remains certain is that relativity already gives us a real kind of time travel, one that moves only forward. The combination of velocity and gravity can carry a traveler arbitrarily far into the future of others. Spend a few years near a massive black hole. Then return, and the universe could have aged millennia. To those you left behind, you would be a visitor from the past, skipping across epochs by taking a shorter path through time's fabric. It is, in many ways, a gentler version of the dream, one that avoids paradox entirely. You cannot rewrite the past, but you can step aside from it, letting it rush on without you. It reminds us that time is not uniform or absolute. It's a landscape, and our motion determines the path we carve through it. And perhaps that's the deeper truth hidden in the fantasy of time machines. We are already travelers, carried forward by the geometry of the cosmos. Every orbit, every acceleration, every gravitational pull slightly shifts our pace. We move together, but not perfectly aligned, each person, each planet, each photon following its own thread through space-time's weave. Some of those threads run nearly parallel, keeping us close in rhythm. Others drift apart the seconds, slower near a planet's heart, faster in the thin air above. Even the atoms in your body tick at subtly different rates depending on their height in Earth's gravity. The universe itself is a vast machine of time, endlessly bending and blending its flow. When scientists study whether wormholes can exist or whether quantum effects forbid closed loops, they aren't only chasing the dream of visiting the past, they are probing the border where gravity and quantum mechanics meet, the very frontier that may reveal how the universe truly stitches time together. Whether or not a time machine ever materializes, this pursuit changes how we see the present. Perhaps time travel isn't about escaping our moment, but understanding it. If the universe is a block, a grand four-dimensional sculpture where past, present, and future all coexist, then motion through time is simply how we experience that sculpture. Slice by slice, traveling through it, even at ordinary speed, becomes an act of perception. Each of us unfolding the story of space-time, one heartbeat at a time. In this sense, the universe itself is the only time machine we'll ever need. Every star, every orbit, every falling particle rides its own trajectory through time, guided by the same geometry that Einstein described. The warp of space-time carries us forward, linking our small moments to cosmic ones. We are all passengers in that great current, moving, aging, evolving, each of us a thread in the vast tapestry of temporal flow. Some paths race faster, some drift more slowly, but all move in the same grand direction. Even the black holes, where time nearly halts, are part of that same continuum, marking its boundaries like still pools in a flowing river. So when we dream of time machines, perhaps what we are really longing for is not escape, but connection, a way to feel the full sweep of time, from the first light of the stars to the farthest future they will ever see. In that sense, the dream is already fulfilled. The universe itself is our time machine, carrying us gently, relentlessly forward. And every breath we take, every moment that passes, is proof that we are already traveling through time together, across the endless and beautiful sea of space-time. If you could step outside the universe and listen to it as though it were a grand machine, you might expect to hear a single, steady beat, a cosmic metronome marking every moment in perfect unison. But that sound doesn't exist. The deeper we look into the nature of time, the clearer it becomes that the universe does not march to one rhythm. It hums with countless clocks, each ticking to its own local tempo, each following its own path through space-time. There is no master clock keeping them all in sync, no universal pulse commanding the flow of existence. Time's rhythm is local, personal, and shaped by motion and gravity. A clock in physics can be almost anything that marks change in a regular way. The vibration of atoms in an atomic clock, the swing of a pendulum, the shimmer of a crystal, the rotation of a pulsar, or even the decay of a single radioactive atom. All of these can measure time. Yet in our real, relativistic universe, no two can ever stay perfectly aligned for long. Einstein showed us why. The speed at which time passes depends on how you move and where you are. A clock in strong gravity ticks more slowly than one farther from it. A clock moving quickly ticks more slowly than one at rest. These are not illusions, they are built into the geometry of space-time itself, because every object takes its own route through that geometry. Every clock lives its own unique story, even here on Earth. The differences are real, though small. A clock in a valley sits deeper in Earth's gravitational field than one on a mountain. The lower clock runs more slowly, its seconds stretched ever so slightly. Place two identical atomic clocks at different heights and let them run for a year. The one higher up will be ahead by billionths of a second. It's barely noticeable, yet measurable, and essential to the accuracy of technologies like GPS. Earth's rotation adds another layer. Points at the equator move faster than those near the poles, which means their clocks run a little slower due to special relativity. Combine motion and gravity, and no two clocks on Earth tick exactly the same unless they share both place and speed. To create a shared time, we rely on hundreds of atomic clocks around the world. Their readings are averaged and corrected for these tiny relativistic differences to form what we call coordinated universal time, the official heartbeat of our civilization, born from the delicate balance of many imperfect beats. Step beyond Earth, and the variety widens. On the Moon, with its weaker gravity and slower rotation, time moves a little faster. On Mars, the difference is greater still. Every world keeps its own pace, defined by its mass and motion. If you tried to synchronize a fleet of clocks across the solar system without accounting for relativity, their readings would quickly drift apart. Space agencies compensate for this constantly when guiding spacecraft, adjusting every signal for the warping of time caused by gravity and motion in deep space. Clocks take even stranger forms. A pulsar, a rapidly spinning neutron star, is one of the universe's most precise timekeepers, flashing beams of radiation with incredible regularity. Yet even pulsars feel the bending of space-time. When one orbits a massive companion, its pulse slows and speeds up slightly as it moves through the other star's gravity. From those shifts, astronomers can weigh stars, measure orbits, and test Einstein's theories against reality. Even the sun is a kind of clock. The nuclear fusion in its heart proceeds at a steady rate, setting the rhythm of light and warmth that reach Earth. But the sun's own seconds are shaped by its position in the galaxy's gravitational field. The same is true for every star. Clocks near the Milky Way's center, where gravity is stronger, run a bit slower than those near the edges. The difference is minuscule from moment to moment, but across billions of years, it matters. Stars age at subtly different rates depending on where they live. And through all this, relativity keeps its quiet rule. Each clock is right within its own frame. When two travelers follow different paths through space-time and later reunite, their clocks may disagree, but neither is wrong. The difference reflects the shape of the journey they each took. There is no single true time against which all others can be measured. Time is local, not universal. This truth unsettles our intuition. We are used to imagining a shared now, a single moment stretching across the cosmos. Relativity tells us that such a global present doesn't exist. Two events that seem simultaneous to one observer may not be to another. This isn't just theory, it's measured and real. The satellites that guide our navigation systems rely on these corrections every second, quietly proving that even everyday technology must bow to relativity's strange music. Think of the universe, then, as a vast web of world lines the paths that every object traces through space-time. Along each one, a local clock ticks, marking that object's personal passage through time. The fabric of space-time ties these world lines together, but it doesn't force them into step. Instead, they form a cosmic mosaic of rhythms, a tapestry of moments, stitched together not by uniformity, but by connection. If you listen closely, it almost becomes a symphony. Each clock is an instrument, playing its part according to the gravity and motion surrounding it. Some play slowly, deep in gravitational wells. Others play faster in the emptiness between galaxies. Together, they create the soft background hum of the cosmos. Not a single tone, but a harmony of differences. Unity, in this sense, is not sameness, it's coherence. This diversity of clocks is not just poetic, it's practical. Engineers and scientists must constantly reckon with it. Satellites, telescopes, and interplanetary probes all rely on timing corrections born from relativity. Pulsar timing experiments detect ripples in space-time, gravitational waves, by watching how these natural clocks drift in unison or fall slightly out of sync. Atomic time standards depend on networks of laboratories comparing and adjusting their clocks, accounting for differences in altitude, gravity, and velocity. Every message we send across the solar system, every precise measurement we make, must be translated between the universe's many tempos. But beyond the calculations, this idea changes how we think about time itself. Time isn't a single river flowing through the universe. It's an ocean filled with countless currents, eddies, and tides, all connected, yet each moving at its own pace. We experience only one small current, the flow that belongs to our planet, our bodies, our hearts. But across the cosmos, every star, planet, and particle drifts along its own stream. Even within you, this principle holds true. The top of your head sits slightly higher in Earth's gravity than your feet, which means it ages infinitesimally faster. It's a difference so small it can never be felt. But it exists, a quiet reminder that time's rhythm changes from place to place. Even within your own body, every step you take, every ascent into the air alters the way you move through time by a fraction, too tiny to imagine. And yet, despite all this complexity, the universe remains beautifully connected. Though every clock ticks at its own pace, they can still communicate. Physics provides the translations, the equations that let one clock's seconds be compared to another's, no matter how different their journeys. This is how we build order out of diversity, how we keep navigation precise, how we measure cosmic distances, how we find harmony in a universe without a single rhythm. Perhaps that is the deeper beauty of the cosmos. It doesn't need perfect synchronization to stay whole. The stars and planets, pulsars and galaxies all keep time differently. Yet the universe still holds together in an elegant, unfolding balance. The illusion of one global time is a kind of truce, a shared understanding, built from constant adjustment, not absolute agreement. So when you imagine the universe's ticking heart, don't listen for one beat. Listen for the many, the slow thrum of stars near black holes, the quick pulse of atoms in your own body, the faint rhythm of light crossing empty space. Each keeps its own tempo, yet together they form a single composition, the music of space-time. And in that music, we find our place, one small clock among billions. marking our moments quietly, faithfully, within the vast and gentle harmony of the universe. For most of us, the passage of time feels unquestionable. We sense its current pulling us forward moment after moment, from childhood to the present and onward into the unknown. We live inside that current, watching memories fade behind us and possibilities appear ahead. The flow of time feels as solid as the ground beneath our feet. Yet when we look at the universe through the lens of modern physics, that feeling becomes harder to defend. The deeper we peer into the nature of time, the more uncertain the flow appears. Does time truly move? Or are we the ones in motion, our minds stitching still moments into a story that feels like movement? In daily life, time seems to have direction. We remember the past, but not the future. We can change what is to come, but never what has been. This asymmetry shapes every aspect of human experience: memory, language, cause, and effect. But when physics examines the same question, the picture changes completely. The laws that govern the universe, from Newton's mechanics to Einstein's relativity to quantum theory, are almost perfectly time-symmetric. That means they work the same whether time runs forward or backward. If you filmed two billiard balls colliding and then played it in reverse, nothing in the equations of motion would object. The laws of physics make no distinction between past and future. The universe, at its core, is indifferent to direction. So why, in our lives, does time feel so one way? The most widely accepted answer lies in entropy, the measure of disorder or the number of microscopic arrangements possible within a system. According to the second law of thermodynamics, entropy tends to increase in any isolated system. Things fall apart. Order decays into chaos. Ice melts, but melted water never spontaneously refreezes into the same pattern. This statistical tendency gives rise to what we call the thermodynamic arrow of time, the only directionality nature seems to care about. But even this arrow is not absolute. The laws themselves don't force entropy to rise. They simply make that outcome overwhelmingly likely. If the universe had begun in a high entropy, disordered state, there would be no sense of direction at all. No before or after in any meaningful way. Time's arrow depends on the improbable fact that the early universe started in astonishing order. From that initial low entropy condition, everything else, stars, galaxies, and the sense of flow we live inside, has unfolded. Einstein's relativity complicates things further. It tells us that space and time are not separate realms, but parts of a single four-dimensional structure called space-time. In this view, every event, every point in space, in every moment in time already exists within that structure. Once something has happened, it is fixed in the geometry of space-time. Just as a mountain peak is fixed in a landscape, the past, present, and future all coexist, each occupying its own coordinates. This idea is known as the block universe, or eternalism. In the block view, time does not flow at all. The universe simply is a vast, unchanging tapestry of events. The sense of motion we feel is not an external process, but an internal experience. Our consciousness moves along a single thread, our world line, revealing one slice of that tapestry at a time. Relativity already tells us that there is no universal now. Two events that seem simultaneous to you may happen at different times for someone moving differently. There is no cosmic clock ticking for everyone. What we call the present is a local phenomenon, a feature of our perspective, not of reality itself. This realization is disorienting because it collides with our everyday experience. We feel the world unfolding. We see the past recede and the future approaching. But in a block universe, all those moments exist at once. The flow is psychological, an effect of how our brains interpret sequences of change. Our minds may be projecting motion onto a static structure, much as film creates movement by flashing still frames in rapid succession. Not everyone accepts this static view. Some philosophers and physicists argue that the universe is genuinely growing, that the past and present exist, but the future does not yet. In this growing block model, time really does advance, adding new slices to space-time as events occur. Others favor presentism, the belief that only the present is real and that both past and future are abstractions. These interpretations restore a sense of becoming and evolution to the universe, something truly happening rather than already written. Physics itself doesn't settle the debate. Relativity is consistent with the block universe but doesn't strictly require it. Quantum mechanics adds new puzzles of its own. In the standard interpretation, a quantum system evolves probabilistically until observed, at which point the wave function collapses into a definite state. That collapse seems to mark a transition, a moment when the future becomes the present. Yet, in the many worlds interpretation, collapse never happens. Every possibility unfolds in its own branch of reality. In the sense of one definite future is simply a feature of our limited perspective within a single branch. Whether or not the universe creates new moments, our brains experience time as an unbroken river. Neuroscience shows that perception lags slightly behind reality by mere fractions of a second as the brain gathers and integrates sensory data into a continuous story. This integration gives rise to what psychologists call the specious present, the short window in which consciousness experiences continuity. Without it, the world would appear as a flickering series of disconnected instants. The mind constructs flow. That same cognitive process explains why we remember the past but not the future. Memory works by encoding information about earlier events. It cannot do the same for what hasn't yet occurred. This asymmetry aligns with the thermodynamic arrow. Information can be stored about ordered states that have since decayed, but not about disordered states that haven't yet taken shape. In other words, we remember because entropy increases. Our mental arrow follows nature's arrow. Still, physics offers no evidence that time itself moves. In equations, time is just another coordinate, like length or width, marking where and when things happen. There's no variable for flow. The sensation of passage may belong entirely to consciousness, a side effect of the way brains evolved to make sense of change. We move through time not because time flows, but because our awareness does. This distinction is more than philosophical. It touches the frontier of modern physics. In the search for quantum gravity, a theory uniting relativity with quantum mechanics, time becomes even more uncertain. Some approaches, like the Wheeler-DeWitt equation, describe a universe in which time disappears from the mathematics altogether. Reality, in that picture, is fundamentally timeless, with time emerging only as an approximation when viewed from within. If true, then time might not be a basic ingredient of the cosmos, but a kind of illusion that arises from deeper, timeless laws. Its flow could be an emergent property of the universe, organizing itself a psychological and thermodynamic mirage floating on top of something still and eternal. And yet, Even if the universe is static in this deeper sense, our experience of time gives life its meaning. The very structure of memory and anticipation, joy and loss, depends on our awareness of passing moments. Without the feeling of time's current, there would be no narrative, no music, no history, no story of self. The human mind may live inside a block universe, but it gives that block texture and direction by living it from within. Perhaps both views are true in their own domains. On the scale of physics, time may be a fixed dimension, already written in space-time's geometry. On the scale of consciousness, it is a river, carrying us from one moment to the next. The universe may not flow, but we do, and that flow is as real to us as gravity or light. From this perspective, our lives are not moving lines on a blank page, but illuminated threads in a timeless tapestry. Each moment we call now is simply the point where our awareness touches the pattern. The past is still there, fixed forever in its own coordinates. The future exists too, waiting in its own regions of space-time. Yet, unseen, we travel through that tapestry, one heartbeat at a time, giving shape to what was always there. So does time truly flow? Perhaps not in the universe's deepest sense, but it flows for us through memory, perception, and change. And in that fragile human current lies everything that makes life feel alive. Physics may see a static space-time, but we inhabit its motion. We are both the stillness and the journey travelers through a universe that does not move, bringing movement to it simply by being. You may never have set foot on a spaceship, never skimmed the rim of a black hole, nor raced near the speed of light. And yet, you are traveling through time right now, this very second. You have been on this journey since the moment you were born, and you'll remain on it for as long as you exist. This isn't poetry or metaphor. It's physics. Every person, every object, every particle in the cosmos moves along its own invisible road through space-time, a journey not just through space, but through time itself. Even when you sit perfectly still, your body and every atom within it are moving forward along the time axis. This motion is steady, constant, and unstoppable. It's what makes clocks tick, what lets memories form, and what gives every moment its sense of before and after. In the language of relativity, your life traces a world line, a single, unbroken path through the four-dimensional fabric of the universe. That line begins at your birth and stretches into your future, recording every place you've been and every second you've lived. No two world lines are ever the same. Even two people standing side by side carry slightly different ones, shaped by their individual motions and by the gravity they experience. The pace of your journey is measured by your proper time, the time that belongs uniquely to you. It's the rhythm of your heartbeat, the tempo of your thoughts, the ticking of the clock you carry within your own frame of reference. And though everyone moves forward through time, not everyone does so at exactly the same rate. Motion and gravity subtly alter how fast time passes for you. If you move faster through space, less of your total motion remains for travel through time. So your proper time slows. Likewise, if you spend time deeper in a gravitational field, time runs more slowly for you than for someone farther from that gravity. This is not a matter of perception, it's how the geometry of space-time itself behaves. In everyday life, The effect is almost invisible. Walking across a room, driving a car, or climbing a hill won't change your proper time enough for you to notice. But with precise instruments, those differences can be measured. A clock on a mountain ticks slightly faster than one at sea level because it sits in weaker gravity. A clock aboard a fast jet runs a touch slower because of its speed. These tiny shifts confirm that your experience of time, your proper time, depends on the path you take through space-time. Astronauts aboard the International Space Station are a living example. Orbiting Earth at 7.7 kilometers per second, they experience two competing effects. Speed slows their clocks, while weaker gravity speeds them up. The result is that they age just a bit less by milliseconds compared to people on the ground. When they return home, they have literally traveled through time at a different rate. Push that further, and the difference grows. A ship traveling near the speed of light for what feels like a few years could return to find that centuries have passed on Earth. A traveler orbiting close to a supermassive black hole might experience hours while thousands of years unfold elsewhere. These are not science fiction fantasies. They're natural consequences of Einstein's equations. From this perspective, time travel is not about building a machine. It's something you are already doing. You move along your world line every moment of your life. The only difference between ordinary and extraordinary travel is how steeply that line tilts through space-time. Whether you're moving quickly through space or sitting still on Earth, you are always moving forward through time. Once you begin to see time this way, familiar ideas like now and later become subtler. Now is simply where you are along your world line. Later is the part you haven't reached yet. Others have their own nows, shaped by their motion and their gravity. The relativity of simultaneity tells us that what is happening at this moment for you may not be simultaneous for someone far away, moving differently. This doesn't change your daily life. We still share moments, meet at agreed hours, and live in sync enough to make sense of the world. But beneath that shared surface, the universe holds an astonishing truth. There is no single universal time. Every being, every clock, every speck of matter carries its own rhythm, its own unfolding. That realization reframes what it means to live. You are not standing still while time flows past. You are moving forward, carving your own trajectory through the geometry of the cosmos. The seconds you experience fast or slow, joyful or heavy, are the measure of your motion through the dimension of time. Relativity turns the ordinary into something wondrous. It tells you that your seconds are personal, that even if you share a life, a room, or a heartbeat with someone, your time is never precisely the same. Each of you follows a slightly different route through the same universe, and yet you meet. Your world, lines cross and intertwine, exchanging moments that are yours alone. When you think about it this way, every connection, a conversation, a shared meal, a glance across a room becomes something more than coincidence. It is a convergence of world lines. Two travelers in space-time meeting for an instant before continuing on their separate paths. When you part, your clocks will quietly diverge again, but the meeting remains, a fixed coordinate in space-time, preserved forever in the geometry of the universe. Even the act of memory fits naturally into this picture. You can recall the past because your brain carries information about previous moments, patterns preserved along your world line. You cannot remember the future because you haven't reached that region of space-time yet. The feeling of moving forward is your awareness traveling from one slice of that line to the next. Whether the entire timeline of your life already exists or is being written as you go is a deeper question, one that physics and philosophy continue to debate. Some interpretations, like the block universe, suggest that your world line already exists from beginning to end, as if your entire life were drawn out across space-time. You experience it sequentially, one moment at a time, but every point is already there. Others imagine a growing universe, where new moments are constantly added, a world still being woven. Regardless of which view is true, the experience of traveling along your world line remains the same, an unfolding of moments, a steady movement from potential to memory. What makes this idea so beautiful is how it connects the cosmic and the personal. The same equations that describe the orbit of a star also describe your walk through an afternoon. The same fabric that bends around galaxies bends around you. Time's relativity doesn't make your moments less real, it makes them more intimate. Your seconds are shaped by your path, your gravity, your motion. They are uniquely yours, belonging to no one else. And though these differences are usually tiny, they remind us that the universe is full of individuality. Every clock ticks to its own tempo, and yet all are part of a single, coherent whole. You, too, are part of that harmony. One rhythm among billions. The cosmos doesn't keep a single beat. It plays a symphony of many tempos. You may never hear that music consciously, but you live inside it. You are one of its notes. Your heartbeat and breath, your waking and dreaming, are all expressions of your own passage through space-time. The universe moves through you as much as you move through it. So when you think of time travel, think not of machines, but of being alive. You are doing it effortlessly, carried along by the structure of reality itself. Each moment you experience, each memory you hold, is a marker of distance traveled. You began your journey long ago, and every thought, every heartbeat, every second, sense has been one more step forward in time. If you could see your entire world line laid out from your first breath to your last, it would be a luminous thread curving through the vast darkness, crossing others, touching, parting, and weaving back again. Somewhere, those crossings are fixed forever. The day you were born, the first time you laughed, the quiet nights you sat staring at the stars, all of them are still there, written into space-time, waiting quietly behind you. And ahead, the line continues unseen, still forming. Whether it is already drawn or still being written, doesn't change what it feels like to move along it. The feeling is real. The journey is real. And it belongs to you alone, even without rockets or wormholes. You are a voyager, not just through the spaces of the world, but through the deep, invisible dimension that gives every heartbeat its rhythm. Time is not something happening to you. It's something you are a part of. The universe carries you forward at every instant, and your only task is to move with it, one breath, one thought, 1 second at a time. And that, perhaps, is the quiet magic of it all. You are a traveler through time not because you wish to be, but because the laws of the universe make it so. The stars move through their orbits, galaxies turn, and you, too, drift forward in your own steady way. So if you're still awake and listening, thank you for sharing this small part of the journey. And if your eyes are beginning to close, let the world slow around you. Let the seconds soften. The stars will keep their rhythm. Time will keep carrying you gently, endlessly, into tomorrow.